Thank you very much. I was already introduced a bit. My name is Maria, and I work at Modus Create. And today I will be presenting you how we approach evaluating. Do you hear me well? Or should I move myself somewhere? Okay. How we approached evaluation of retrieval in RAG, as we found this component of the system the most in need of evaluation. So yes, the bit of structure, maybe if I have, do you see my mouse? Oh, yes, you probably do. That's perfect. So my company is called Modus Create. Previously, it was Tweag, which was very connected to open source community. And thus our approach to solving problems is trying to be very open and like give back to the community that we grew from. So in there, we formed several technical groups, and one of them being generative AI, who is led by totally amazing Nur. So I have a privilege to be a part of this generative AI team, and the work that I will present to you is done by both of us and also Joe, yes, who is in here. Yes, so that's a short. I was supposed to start my timer because without it, I am lost. Okay, so a bit about Tweag, a bit about Nur, that she's fantastic, a bit about me maybe. I started the journey in data science after after my PhD, which was in fluid dynamics, especially exactly the mathematical modeling in fluid dynamics, and that's why I found the data science very interesting. And then from there, I grew interest also in functional programming and all different kinds of things related to data and its processing. So that's also why I'm here. Yes, and since we are talking about RAGs, it's nice to introduce them. So what are RAGs and why do we need them anyway? RAGs are the systems that consist of a large language model and some kind of data retrieval. So in here you have like example of ChatGPT 3.5, which was done a few months back. So you might find some things funny or obsolete until then, since this discipline is very fast-paced. So we asked ChatGPT who won 2024 Asia Cup. And ChatGPT did not know, obviously, because it was trained until January 2022. So it does not have this kind of information. So why do we need to augment this generation of our LLM? First, that, as you've seen on the previous slide, the LLM have a learning cutoff, so it will not be able to answer you questions that answer is found later than the learning cutoff happened, which is quite important. For example, in fast changing information domains, like if you would like to create, for example, chatbot over your documents database, and you still add more and more documents, that is why you will not get information about them in your even fine-tuned language model. And if we come to fine-tuning, fine-tuning is costly, as you have to somehow retrain the model. Even if they are the top layers of this model, it still takes some time, and you have to have data to do that. So it's additional thing that you have to take into account. On the other hand, adding the context to the prompt to LLM is relatively easy. And you can find relevant context, for example, with semantic search. And we'll be talking about this in a bit. And here you have some graph of how you can approach it. So you have a document base that you put into a vector database. Here we used Chroma. You ask your question as a user, and then Chroma gives you some ensemble of documents that are interesting for this question, and gives it to prompt, and this prompt goes to your large language model. So why semantic search? Why is it so awesome? And sometimes not. That is because you change not the structure, you represent, that's the word I was looking for. So you represent your textual data in terms of numbers, and you have some additional model on that words or sentences or parts of, or even paragraphs that will change your text into those vectors. And as we know, it's much easier to compare vectors to each other as you have several measures to do so. So if you embed the document into a vector database and you query this database, you try to find the vector that is closest to the vector representing your query. So it's like you are changing the changing from text to vector spaces, which are easier to handle. Yes, so that's the semantic search. You might already see that in a semantic search, as you are comparing the meaning of sentences or paragraphs, there are some information that might be lost. For example, the actual names, like how can a embedding figure that you are meaning something which is a name of a particular thing and not something more general. And this will be a problem later. And back to our RAGs, because you definitely have seen the RAG before if you played with ChatGPT or right now, like 4 and right now 4.0. It would give you a more informative answer on your question. So in that case, 2024 Asia Cup, you would get an information that it did a quick search and it was not able to find the information. So it's like it tried to retrieve the information, but it didn't find it. So it gave you the results that it cannot find it. But if it would have found it, then you would get the summary of who won the Asia Cup, maybe with some more information. And the concept was so nice that we wanted to build our RAG too. And we started with building a RAG over Confluence database, because if you work in some company that has a lot of documents, it's sometimes hard to figure what they actually mean and hard to find something there. Sometimes keyword search helps, and in case of Confluence at that time, it helped a bit, but we hoped that we can create a more conversational way to figure what's in our Confluence database. So we built our RAG. And here you have an example of the question we asked. It was, what does OSPO stand for? And OSPO is Open Source Program Office, and we were very happy that our RAG found the information. So yes, we high-fived ourselves. And apart from Confluence, which apparently when we tried to ship this feature internally, apparently Confluence already shipped it. So I think it was in December last year. So Confluence added the feature of semantic search to its interface. But yes, we already had it, so we're also happy that we went through this path of exploring how to build this kind of system. But apart from the internal documents like Confluence, we can also use it to enhance user experience in open source. And in our case, Bazel, which is a build system, open source language for build systems, is notoriously known as that has not so good documentation, let's say, very mildly. So we tried to create a RAG that will help people use Bazel documentation. And as you might also imagine, the constraints on Confluence and Bazel were different. As you have an open source documentation already, you can use models that are that do not have those privacy guarantees like you would have to have if you try to do your internal company documentation. Yes, so the models, the LLMs underlying were also different. And the very, very rough graph of RAG is that we have retrieval generation, like retrieval. We send some query. We retrieve the data that is most relevant to this query from the vector database. Then to the LLM, we send the query and the context, and we generate the answer to a user. So that's the most basic case. Of course, every arrow might be expanded, and you can put some more how would you say it? Like more complex handling of everything that you see in those arrows. Okay, so we were quite happy with this one example and several other as well. But then we figured that for some of our queries, the RAG system is giving us very bad results. So we figured that we have to have some way of evaluating that, because otherwise we will be changing some parameters and it will be basically a random movement of parameters. So like here on this slide, you have the programmer that is experiencing errors and errors and errors and one success, and they are very happy. And as you know from probability, it might have been 1 over, I don't know, 6 chance of the success. So you don't really know if your approach is good or bad. And that is why if you only eyeball over your experiment, you do not know if the performance over some other question may be worse, may degrade. You do not have an experiments tracking mechanism, so you cannot like go back to your previous experiment and know that, oh, well, in this case of this parameter, we had this result. Another thing is you do not have solution space or evaluation metrics, which will be important to figure how your RAG system performs. And why? It's just garbage in, garbage out, as usually with the data. If you put some irrelevant retrieved information to the system, it will not give you the result you expect. That is why we have to know that this retrieval part, which we found particularly hard to optimize, that is why it has to be checked. So what we decided to go with is to create some kind of like a loop that will help us evaluate how should we build the retrieval of the RAG system. So first we created a benchmark. We defined parameter space for this evaluation metrics and some ways of evaluation tracking. And we will go through each of these parts in the next slides. So starting with the benchmark. We had 3 ideas how to create a benchmark over the document database. First, you can have just questions and nothing else. Then from that, you can evaluate, like you can use metrics that are LLM based, because, or you can have a human labeler who will label if the question was answered good or bad. You can have pairs of questions and answers all written in plain text. But what we found the easiest and like already the best researched is pairs of questions and relevant documents. I will tell you why. But before that, the problem is that if you have questions and relevant documents, you might have your benchmark might not be as big as it would have been if you used pairs of questions and answers that are auto-generated, for example. But what is not easy is that you would like to have questions that will actually be asked by users of your application. So like in this beautiful example, here is the Gaussian ball. From the Confluence database, you would rather ask questions like, how do I apply for a day off? Or what are this quarter's KPI if someone is interested in that? But you would rather not ask about what can you feed to a cat. And some parts of this process of creating a benchmark can be automated with large language models. One of that being generating questions over documents, which we finally did, but it was not our first shot. And the second one, if you have already questions given by users and relevant answers or relevant documents, you can reformulate questions using LLM, because people can ask the same thing in various ways. So if you use a model different than the one that, so if you use model for reformulating different than the one that you are using for your drug, it might make sense to like expand your benchmark with this kind of questions. Yes, and that's how what I mentioned before, that first we decided to use human-generated with reformulated questions, because we found that that they will be most likely somewhere here, right? So in the bulk of this bell curve. But you can also use LLM-generated questions, which will be our small, maybe Easter egg after that. Second thing, after the benchmark, the parameter space. What can we change in our retrieval to see the outcome, how the model changed, how the retrieval changed. So in case of ChromaDB, there were things called collections. It's like a table in relational database. And those collections we had to create from for every, like it would be another parameter, because for the collection, you embed the same database of your text, but into different vectors, because you can use, for example, different embedding model, chunking model, and so on. So the second parameter, which is actually meaningful, was which embedding model do we use? So what way do we use to change our text into vectors? And there are several available models that you can use. We even tried a bit for fun, but not you might guess what happened if we try to tokenize by word only and not by sentences, which I find very interesting, because it's like a progress in the recent 5 years. I would say, like 5 years ago, I would have done the same thing with the different embedding model. So I'm very happy that we have the sentence-based right now. Another thing that we can play with is chunking model. So the way we split text, usually the texts like, for example, in our Confluence are few thousand characters, 3,000 words long. So you don't want to have this whole given to a large language model in a prompt, because some of the models do not work well with a needle in a haystack problems. So if you put there too much things, it will not be able to capture the actual thing that you are interested in. And another problem is that they might have the context window of your LLM might be too small to put this large of a context. Then for retrieval, we also had top K, so the number of retrieved documents. And another thing that we can play with is preprocessing model. So how you play with your query, because if you put query to LLM like, oh, please tell me what OSPO is and create a JSON with the key and the value of that I want you to do, then the JSON part of this query is irrelevant to our retrieval, right? Because it's like just a presentation of your results and not really the question per se. Yes, where am I? So from this, we can go to see how we can evaluate the retrieval. And what we found, like the most convenient, that would be easiest to explain, are the metrics based on information retrieval. So the classical, like traditional machine learning metrics. If you have a labeled data set, and then you can just say if it was retrieved or not. So you have like 0-1 situation. Either it is retrieved or not retrieved. And from there you can use metrics like recall and precision at k because you took only top k most relevant documents, right? So you always have it at k. On the other hand, you can have LLM-based evaluation, which gained traction, I think, in the last couple of months. So for this, you can have, for example, context relevance, which is a ratio of relevant to total sentences in the retrieved documents. Sentences meaning that we tokenize it with sentence. You can also have context recall, which will be similar to the recall in the classical sense. And just to set our minds on the track how to do this evaluation, starting with the query and having the context, we check how relevant was the context? Was it relevant to the query? And that is the part that is really of interest to us right now, because we have trouble with getting the right documents retrieved, right? There are some other metrics that you might check once you have the context already solved, but we will not be going into that. So this is the one that is of interest to us. And as I mentioned, we went with the information retrieval metrics just to have it have least moving parts. But of course, you have libraries that provide with LLM-based metrics. For the experiment tracking, we used like our custom setup. It's just a super schematic view of how we did that. DVC is a version control. Chroma I mentioned before, so that's how we handle data. The experiment parameters are the JSON that I showed you a bit before. Version control of the code, we have Git and GitHub for that. And for experiment tracking, we used MLflow, which was quite convenient for that. And it was all written in Python, so it was also easy to develop and see. And how we went about our evaluation. So first, there are parts that have to be given by the user, and there are parts that are playing automatically. So first we had to build a benchmark. And as I said, we did it more manually. We asked people to give us questions that are relevant for them to figure from the Confluence database and Bazel database. And we treated that as a ground truth. Then we create some starting parameter set. And with this parameter set, we run the retrieval. In running the retrieval, we also mean that we first have to create a new embedding. So we have to create the whole, what was called their collection in our database. And on that, we can run retrieval. Once we have retrieved documents, the situation is simple because we know the ground truth. We have the retrieved documents, so we use the classical measures. And if we find it up to our standards, then we can end. If no, we can check new parameters. We can play with them somehow. So that was our idea, and we did that. For embedding and chunking models, we used several ones that were available on the internet, obviously. So here they are. We will not be going into details, as I must speed up a bit. And for benchmark, we used user questions and questions reformulated with ChatGPT 3.5 at that point. Okay, so now here is the graph, which we were pretty proud of, but its density of information is striking. So don't worry, I will try to go for that. I think the only thing that we did not use, which could be used, is like a pattern of the bars. So yes. So what does it mean? RC is from here, recursive character text splitter, the chunking model. ST is sentence transformer token splitter. So there's only one with sentence transformer and not recursive character text splitter as a chunking model. Then we had different embedding models, which are denoted in here on the x-axis. What we are looking at generally is average recall, because we want to have all the documents that we put in our benchmark, we want them retrieved because we know that they are the good ones. And for that, we used original questions only, and we used reformulated questions. So it was the bigger benchmark, right? Because we reformulated it, so we could put 10 times more questions there. Okay, and those two compare quite like intuitively, right? Because you have reformulated questions, so it is most likely that some of this reformulation will give you the right result. So average recall will be higher. And this setup, I think it was even the standard setup for the library that we used. It gave us the best result. And further down the road, it was a bit worse and worse. So in here, I compared different embedding model for then all mini LM, but with different splitters, right? And the RC splitter, so recursive character text splitter, was found to be better. And with that, like we have different sets of parameters that we can compare and the metrics that we can compare. So also, again, our space that we as humans have to parse and make a decision on is quite big. And one more thing about the metrics. Here is a very rough example of what we did recently, because we didn't give up on trying to find the best retrieval. So in here, you see two different LLMs used in RAG system. One is Claude, one is Llama 2, I think it was 13 billion. And 1 to 3 are different ways we construct benchmark. This time we constructed benchmark based on our documents. We created with LLM questions that might be asked about this particular document. And one of the ways we did this also included in retrieved context the actual answer, because we knew from which it was generated. So as you might guess from this picture, if you have a inquisitive eye, you see that there is also always model of number 2 has higher metrics in every single thing, because that's the model that actually takes the relevant documents that we are sure that are relevant. And the two other models are showing the free search for relevant document, but different data processing. One is with the titles, it was on Confluence data, so the title of the article, and one is without title of article, which, as you might see, the improvement is rather infinitesimal than important. So we are still in a place where we have to figure how to make the retrieval better. And I have some ideas, and I would really like to hear what you have to say about that. But to finish that, the key takeaways from that talk that I would like you to take with you is that you have to evaluate your system, and just simple eyeballing over, well, that works, it's not really enough. And there are many frameworks, tools, and the space is developing all the time, so you might find something that will fit your particular problem. Thank you very much.